So, we have looked at reaction rates for chemical equations, much like the ones we've been looking at since early in our chemistry careers. These equations have reactants on the left side and products on the right side. We also have the arrow that tells us that reactants become products. Here is our normal-looking chemical equation. We can see that dinitrogen tetroxide reacts to form 2 moles of nitrogen dioxide. We can talk about the forward rate of the reaction in simple terms using the stoichiometry. Note that this isn't exactly the same thing that we did in the kinetics section, but it is basically the same idea. We can say that the rate equals the concentration of dinitrogen tetroxide times a rate constant K. Now, let's imagine that this reaction could also go in the reverse direction. That is, that 2 moles of nitrogen dioxide could react to form 1 mole of dinitrogen tetroxide. We can denote this by using a reverse arrow. We can also write a rate reaction for the reverse direction, using stoichiometry as we did for the forward reaction. Reactions that move in both directions like this are called reversible reactions. If we put dinitrogen tetroxide into a container and allow it to react, it will move in the forward direction. However, once nitrogen dioxide starts to build up, it will react to form dinitrogen tetroxide. So dinitrogen tetroxide will be disappearing as it turns into nitrogen dioxide, which will be disappearing as it reacts back into dinitrogen tetroxide. If we leave this reaction alone, the concentrations will change over time as we see in this graph. Notice that in the beginning, the change in concentration of both reactants and products is rapid, but they will both eventually settle to a constant concentration. This state is called equilibrium. The back and forth has not stopped, but the amount going in one direction is balanced by the amount going in the reverse direction. The graph of the rates over time show that they converge on a single value. At that convergence point, we would say that the system is in equilibrium. We can also say that the rate of the forward reaction is equal to the rate of the reverse reaction. Chemists use a system for describing the concentrations of reactants and products in a reversible reaction at any given time during that reaction. This is called the reaction quotient and is symbolized by the capital letter Q. For this generic reaction, the reaction quotient is equal to the concentrations of the product side with their stoichiometric coefficients as exponents divided by the concentrations of the reactant side with their stoichiometric coefficients as exponents. Once equilibrium has been reached, the concentrations and thus the Q value remains the same. This is known as the law of mass action. Additionally, Q can be expressed in terms of the concentrations of reactants and products or in partial pressures when they are all in the gas phase. Chemists represent the unchanging equilibrium value of Q as the capital letter K, which is the equilibrium constant. When Q equals K, then the system is at equilibrium. It is important to note that K and Q don't tell us anything about how fast a reaction will reach equilibrium. They only relate the concentrations of reactants and products as they approach equilibrium. K and Q are also unitless because they are a ratio. This also suggests that we can tell the direction of a reaction based on the relationship between K and Q. If K is larger than Q, then the reaction will proceed in the forward direction. If K is less than Q, the reaction will proceed in the reverse direction. Let's look at a chemical equation and do some calculations based on what we know so far. For this reaction, Kc is 0.64. Examine this chart of data for the reaction. We can see that for experiment 1, the Q value is 0.040. Since this is less than K, the reaction is still predominantly happening in the forward direction. It has not yet reached equilibrium. Q for the reaction during the second experiment is 1400. Since K is much lower than this, the reaction will proceed in the reverse direction. Ultimately, K and Q will be the same once the reaction has reached equilibrium. Read and work through pages 82 through 84 in the workbook. K can be expressed in terms of concentration, or in terms of partial pressures, just like Q. This implies that substances that are not in the gas or aqueous phases will not be included in the expression for K. Thus, an equation that looks like this will have an expression for K that looks like this. Notice that the solid isn't included in the expression. We'll discuss solids and equilibriums later. For now, we can ignore anything that isn't a gas or aqueous. For equations with all the substances in the gas phase, We can write K in terms of partial pressures of all of the gases. Additionally, gases can be considered in terms of concentration, such that 5 moles of gas in a 1 liter container is 5 molar. Consider this reaction in equilibrium at 430 Kelvin. All of the reactants and products are in a 10 liter container. There are 0.54 moles of hydrogen sulfide, 0.76 moles of oxygen gas, 3.4 moles of water, and 2.2 moles of sulfur dioxide. What are Kc and Kp for this reaction? For Kc, we can divide each by 10 liters to get moles per liter. Then we can set up the Kc equation. We get 4,370. We can convert Kc into Kp by using the ideal gas law. Since PV equals nRT, if we divide by V, we get molarity times the gas constant times the temperature, which equals the pressure. Thus, we can use the concentrations from our Kc to calculate the partial pressures of each substance. We can then solve for Kp in the same way as we did Kc. And we get 123. If we do a little math with the ideal gas law, we can derive a direct equation that can be used to calculate Kp directly from Kc, such that Kp equals Kc times the gas constant times the temperature to the delta N power. Delta N is the difference in the molar amounts of products versus reactants. So for this equation, delta N would be 1. Let's look at a calculation. Consider this chemical equation. At 298 Kelvin, the Kp for this reaction is 2.26 times 10 to the minus 22nd. What is the Kc for this reaction? We can use our Kp to Kc equation, which also works in the opposite direction if we need it to. We put all this together, along with the appropriate gas constant, and we get that Kc equals 2.6 times 10 to the negative 23rd. Read and work through pages 85 through 89 in the workbook. Now, let's consider what happens when we disrupt a system at equilibrium. Because a chemical equilibrium is a dynamic balance, if we unbalance the scale on one side or the other, the equilibrium will respond and adjust. This is called the Chatelier's principle, which states that if an equilibrium system is stressed, the system will experience a shift in response to that stress that reestablishes equilibrium. Consider the equation where hydrogen gas and iodine gas react to form hydroiodic acid. If we increase the concentration of hydrogen gas, then Q will decrease. To reestablish equilibrium, the forward rate of the reaction will increase and a new equilibrium will be established. However, the Kc for this reaction doesn't change in the presence of changing concentrations. Thus, if we add more hydrogen gas, the end product will have more hydroiodic acid and less iodine gas than before. If we remove hydroiodic acid, then Q will decrease again and push more reactants into products to reestablish equilibrium at the same Kc value. The final concentrations of reactants will be lower, but Kc will not change. We can do the opposite of this and get opposite results, and drive the reaction back towards the reactant side. Regardless of in which direction we disturb the equilibrium, Kc will remain unchanged. For gas phase equilibrium, there are some additional things to consider. Because the concentration of gas phase substances is directly proportional to their partial pressures, any changes in the partial pressures of any reactant or product are the same as changes in concentration. As with Kc, Kp is disturbed in the same way by changes in the concentrations or partial pressures of reactants and products when any of these substances are added or removed. These changes are analogous to the changes we saw in Kc. However, changes in the volume of the container will have different effects depending on the stoichiometry of the reactions they contain. With our hydrogen gas example, if we express all of the substances in terms of partial pressures, we get our familiar Kp equation. If we decrease the total volume of the container, the partial pressures of each reactant and product will change proportionately to their moles. Thus, if we decrease the container by a factor of 3, this will increase the partial pressure of each substance by 3. When we do this, we get no change in the resulting equilibrium because this new Q value is still the same as K. However, for a reaction like this one, if we do the same thing, we get a Q that is 3 times higher than Kp. And will result in the reaction moving toward the reactant side. Why did this happen? In our first example, the ratio of moles of reactant to product was 1. Thus, regardless of which side of the reaction was favored, the same number of moles would be present. What about for the second reaction? As we shrink the container, it will push the equilibrium towards less total moles of gas. Because the reactant side is less moles than the product side, the equilibrium will shift in that direction. What direction would you predict for this reaction if we reduce the total volume by 3 times? What else might affect a chemical equation? Oh yeah, heat. We know from thermochemistry that heat can work as both a product or a reactant. For endothermic reactions, heat is a reactant, and for exothermic reactions, heat is a product. For the purpose of equilibriums, this is even more helpful. If we add heat to an exothermic reaction, just like adding more products, it will push the reaction back towards the reactant side, and the opposite for endothermic reactions. During our study of kinetics, we looked at how a catalyst can lower the activation energy of a reaction and make it proceed at a faster rate. How do you think that will affect a system in equilibrium? If we add a catalyst to an equilibrium, what we find is that there is no change in the equilibrium. This is because a catalyst can increase both the forward and reverse reactions. So the system will reach equilibrium faster, but it will still have the same Kc or Kp value. Read and work through pages 90 through 93 in the workbook. Ice tables. We know that no matter what concentration we start with in a reversible reaction, eventually that reaction will reach equilibrium. This means that we can relate the changes in concentration of reactants to changes in concentration of products, much like we did for relative rate laws in kinetics. For the decomposition of ammonia, we can say that as the reaction proceeds to equilibrium, the concentration of N2 will increase by an amount, say X. We can relate the corresponding changes in concentration based on their stoichiometry as we have done before. The negative sign here reflects a decrease in concentration. For the whole reaction, we can say that the concentration changes are reflected by X in these ratios. Now let's use this information to set up an ICE table. ICE is an acronym that stands for initial concentration, change in concentration, and equilibrium concentration. We can use what we know about concentration changes and the formula for an equilibrium constant to figure out Kc for a reaction. Let's try it with this one. Aqueous diatomic iodine can react with iodine ions to produce triiodic ions. The Kc for this reaction would be represented by the concentration of I3- over I2 times I-. If the initial concentrations of I2 and I- are 1 times 10 to the minus 3 molar, let's fill in an ICE table with what we know from the starting conditions. These are based on the one-to-one stoichiometry of the equation. So the concentration of I2 and I- will have a negative X change, and the concentration of I3- will have a positive X change. Make sure you understand why the different X's have those signs. So, at equilibrium, the concentrations will have changed by a difference of X. We are told that the I2 concentration has changed to 6.61 times 10 to the minus 4. So X must be 1.0 times 10 to the minus 3 minus 6.61 times 10 to the minus 4. That gives us 3.39 times 10 to the minus 4 molar as X. We can now fill in the rest of the ICE table. This gives us our concentrations at equilibrium. And we can use these to calculate the value of Kc for this reaction. A little bit of math and we get 776. Let's look at our old friend, hydroiodic acid. In this case, We know that the Kc for this reaction is 64, and the initial concentrations of hydrogen and iodine gas are 1.9 molar. What is the concentration of H2 gas at equilibrium? We can fill out an ice table with what we know. 1.9 molar for the starting concentration and 0 for hydroiodic acid. The changes will be this. Why is the concentration change of hydroiodic acid written as 2x? This gives us expressions for the concentrations at equilibrium. Let's put these into the expression for Kc. We can solve this for x and get 1.52. We can then use the equilibrium expressions with this value to solve for the equilibrium concentrations of all the species involved. Read and work through pages 94 through 100 in your workbook. Next time, we will look at acids and bases and how they act as part of equilibriums.